Engineers continued with the jet firing development flight test objective that began on flight day 12. Today, teams demonstrated the low portion of the reaction control thruster firing time range. This test objective is designed to exercise the reaction control system jets in a different configuration to model how thruster jets will be used during the Artemis II mission, furthering our understanding of spacecraft operations before we have crew on board. As part of planned testing throughout the mission, the Guidance, Navigation, and Control Officer, also known as GNC, performed the 6th of 8 planned tests of the star trackers that support Orion's navigation system. Star trackers are a navigation tool that measure the positions of stars to help the spacecraft determine its orientation. The star trackers continue to provide excellent data to develop our required navigation solutions. Engineers will characterize the alignment between the star trackers that are part of the Guidance, Navigation, and Control System and the Orion Inertial Measurements Units, by exposing different areas of the spacecraft to the sun and activating the star trackers in different thermal states to determine if the temperature differences induce any changes. The inertial measurement units contain 3 devices, called gyros, used to measure spacecraft body rotation rates, and 3 accelerometers used to measure spacecraft accelerations. A new flight test objective was added to flight day 14 to collect additional information on the thermal characterization of Orion. During a majority of the mission, Orion is typically in a tail-to-sun attitude, meaning that the solar arrays face toward the sun to generate power. This flight test objective purposefully orients Orion outside of a perfect tail-to-sun attitude by up to 20 degrees in order to evaluate the spacecraft and gather additional data. Currently, when Orion is out of the tail-to-sun attitude for more than 3 hours, a 10-hour tail-to-sun recovery period is required. This additional flight test objective will help engineers understand the range of Orion's thermal performance to incorporate into Artemis II and beyond. Time and distant retrograde orbit allows engineers to test the spacecraft and its systems in a deep space environment ahead of future missions with crew. Distant retrograde orbit is a highly stable orbit where little fuel is required to stay for an extended period. While visiting a distant retrograde orbit allows engineers to capitalize on an orbit that was comprehensively studied as part of mission plan for earlier agency efforts, future Artemis mission will visit different orbits. On Artemis II, for astronauts in Orion will travel around the Moon and fly several thousand miles above the lunar far side before trekking back to Earth. On Artemis III, the first Artemis mission to the lunar surface, Orion will venture to near rectilinear halo orbit, an orbit balanced between the Earth's and Moon's gravity that hangs almost like a necklace from the Moon. The orbit provides access to the Moon's south pole, where 13 candidate landing regions have been identified for future Artemis missions. Just after 4 p.m. Central Standard Time, Orion was over 264,000 miles from Earth and nearly 46,000 miles from the Moon, cruising at 1,790 miles per hour.